So what I want to do in this video is I want to introduce you to the ideas of force and motion. And really this particular presentation is what we might consider to be the very first stages of understanding the concepts of biomechanics within any kind of sports science program, and particularly in this case for ASP students who are studying this within their anatomy and physiology course. So first of all, let's just define our terms. Let's make sure we understand, we know what we mean by force first of all. A force is a push or pull that tends to alter the state of motion of a body. The state of motion of a body. Now, when I say a body, I don't necessarily mean a human body, although indeed I may well do. It really means an object. So really it's either push or pull that tends to alter the state of motion. And we must pay kind of attention to this word tends to change the state of motion of the body, because of course that push or pull needs to be forceful enough to overcome the kind of resistance of that body. And if that body has a large mass, for example, it will have a lot of resistance to change its state of motion. If it's heavy and it's not moving, we have to push it hard, and if we don't push it hard enough, it doesn't move. So we have a tendency to alter the state of motion by the application of a force. And I also want you to understand that a force has a unit of measurement, and that unit of measurement is referred to as a Newton. And a Newton, of course, named after mathematician, scientist and philosopher Isaac Newton. That Newton is the amount of force required to accelerate 1 kilogram of mass by 1 meter per second squared. And that's how much we mean by 1 Newton. It's the amount of force required to move 1 kilogram of mass 1 meter per second squared. So when we refer to a Newton, as the unit of force, that is what we are referring to. Okay, we're going to have a look now at the idea of motion, and I want to introduce you to 3 types. I'll quickly state what they are now. We're going to have a quick look at the concept of linear motion. We're also going to study and hopefully understand the idea of angular motion, and I also want to show you the composite form of motion, which we refer to as general motion. So let's make a start on that immediately. So here we go. What I've got as I scroll down here is an example of an athlete taking part in one of what we refer to as one of the sort of toboggan events, or the Winter Olympic toboggan events. And this example specifically is the example of the luge. I would encourage you within your ASPE exams, the word toboggan often kind of gets you the mark, toboggan. So I would kind of consider writing this as toboggan rather than luge. But what we essentially have here is we have the description, in this case, of all parts of the body, are moving in the same direction, at the same time, at the same speed. And this rather lengthy definition is actually a definition of what we refer to as linear motion. And it makes sense. Linear, kind of straight lineness, for example. We have the idea that this entire person, this entire body, is moving in the same direction at the same time at the same speed. In other words, it's heading in that direction at a certain velocity, and it's going in that direction. And because all parts of that body are going in that direction, we refer to that as linear motion. And we also need to explain what causes linear motion. What causes linear motion? And the answer to that question is that what causes linear motion is a direct force. A direct force. And a direct force, what do we mean by that? Well, a direct force passes through the centre of mass of the body. Passes through the centre of mass of the body. So let's have a look at that as an example. What I've got down here is I've got this shot put is being released by this putter, by this athlete. And what we can see here is that the hand is applying a force through the centre of the ball. Just there, let me do that in a slightly different colour, just a little bit darker. We've got a force being passed through the centre of the ball. And as a result of that, that object is going to follow, do again a different colour, is going to follow this trajectory. Now of course it's not quite a straight line because gravity is acting on it to bring it back down to Earth, which will land somewhere over here. But this object has had the force applied through the centre of mass. Through the centre of mass, and therefore the ball will not spin. It will travel in a trajectory which we would call an arc. And a term that you'll use next year is if we have this arcing trajectory, we actually refer to that as a parabola. A parabola. And it's also what we refer to as a symmetrical flight path. And you might not think it's symmetrical like this, but imagine if we continue the arc on that way, we'd end up with effectively a symmetrical arc. And this is what we mean by linear motion, that a body will travel, all parts of it, in a straight line or an arc, with all parts of it moving at the same time, at the same speed, in that same direction. And we achieve that through this idea of a direct force through the centre of mass of an object or of a body. Well, that's our linear motion, fine. Well, let's look at a different example. Of course, if I take this tennis ball here, and if, for argument's sake, I do strike the ball at this point, and I strike through the centre of mass of that ball, of course, that ball is going to produce linear motion. It's going to produce linear motion, just as we've described previously. But what I'm going to argue here is that we're not passing that force through the centre of mass of the ball. Let's say, for argument's sake, we're going to strike the ball at this point here. Imagine we're hitting the ball in this direction of motion. We're going to strike the ball here, and we're going to apply that force there. Okay, I'm not travelling through this centre of mass. Instead, I'm hitting off centre. And when we say we are hitting off centre, or off the centre of mass, we have a name for this type of force. And that type of force we refer to as an eccentric force. An eccentric force. An eccentric force. And any kind of eccentric force which is applied off the centre of mass of a body, we actually refer to that as an example of angular motion. Angular motion. And angular motion is when a body moves in a circle or in a part circle about its axis. Okay, so you can see with this ball, I'll just do an illustration of it here. This ball, here's its axis of rotation. This ball is in fact, because it's been struck here, this ball is in fact going to rotate in this direction. Okay, and of course if we are travelling that way, we would actually give this a name, which of course is topspin. This is how we would generate topspin, for example. Topspin is generated by applying an eccentric force and producing spin, or angular motion. And finally, for this video, I want you to understand that we can combine the ideas of linear motion with those of angular motion. In fact, many sporting performances rely on a combination of both linear and angular motion. So let's just look at that as an example. Here we've got Usain Bolt. I'll kind of use pink here. His torso, which is roughly this bit of him here, that part of his body is going to move in a straight line. It's going to run in that direction. It's going to move with linear motion. Linear motion. However, his arm, for example, is going to rotate. It's going to rotate here, and then it's going to rotate back. His leg, for example, let's look at the knee here. His leg is going to rotate under there at the knee, and then it's going to rotate back again to make the leg straight. So therefore we have both linear but also angular motion. So this is an example of the arms and the legs sort of part spinning circles, angular motion. And when we get a situation where we've got linear motion plus angular motion, we end up in the situation as I described right at the start with the concept of general motion. General motion. And general motion is the sum of both linear motion and angular motion. Linear motion plus angular motion equals general motion. In fact, let me write that in. Linear motion plus angular motion equals, and of course our answer is general motion. General motion. Okay, thank you for listening. I hope that's been useful, and I'll catch you next time.